We're going to
Look
start
at this. This is all homework.
the next section, which is translations and vectors. And I think you're going to find this to be pretty easy.
Are we just
Okay.
doing this section?
We're just doing one section, 7.4. If you finish ahead of time, I'll give you time in class to work on homework. All right, so is everybody on?
Wait, I'm sorry.
We're starting at 7.4.
Oh, we've started. Yeah, we started.
Okay, so we're on page 421. Is everybody there? And it's called Translations and Vectors, okay? And Garrett, would you read what the translation is at the top of the page?
A translation is a transformation that maps here it is. Maps every 2 points P and Q in the plane to points P prime and Q prime.
So that the
So
following
the following properties are true. 1. P prime is equal to Q prime.
So in other words, the distance between P and P prime is equal to the distance between Q and Q prime.
PP prime and QQ prime, they're
Parallel.
or PP prime and QQ prime are collinear.
Okay. Okay. Okay, so they're either going to be parallel, or if they're already collinear, and then so in other words, if the whole line is moving, translating, then they'll be all collinear, okay? Or the line is moving this way, then they'll be parallel. Okay, so guess what this kind of translation is? An isometry. So what does that mean?
It means
It's a rigid transformation.
it's got a theorem for
Yeah.
a theorem that
It's a rigid transformation.
Okay, so all right, so let's look at the proof that they have for this. Let's just read through this. This is theorem 7.4, and it can be proven as follows. Okay, so now remembering your parallelograms, right? It says you're given that PP prime is equal to QQ prime, so the sides, basically the sides of that quadrilateral are congruent, right? And they're parallel. So do you guys remember a theorem about if a set of opposite sides are parallel and congruent? What do you have?
a rhombus.
Well, I mean a rhombus, but more generally, you have a parallelogram. Okay, so that is a parallelogram. I mean, it could possibly be a rhombus. We don't know for sure, but it's certainly a parallelogram.
A
Triangle. It's a figure.
Okay, so let's read through this.
It's
It
a
says the opposite sides, which implies that's a parallelogram. From this, you conclude that PQ is equal to P prime Q prime. Okay, and therefore, it's almost like CPCGC, except it's we're talking about a parallelogram. So the opposite sides would be congruent. Okay. All right, now this says you can find the image of a translation. Okay, by gliding a figure in the plane. Another way to find the image of a translation is to complete one reflection after another in two parallel lines. Okay, so you see what's happening there. You see the blue sort of pie-shaped looking thing going over line M. That becomes the red image. And then again, it goes over again and in, and now it's got the green thing. And you notice that from the blue shape to the green shape, you have a translation. So if you do two reflections in parallel lines, have to be parallel lines, then oh no, something's sliding downstairs. Then that's the same thing as a translation.
Couldn't you do 2 rotations?
Right. So the 2 rotations. Remember that you could get a reflection also with 2 rotations, but the line of reflection, right, was, I don't know, there was something about the, it was half the rotation. So there's definitely tie-ins with all of this. Okay, so let's take a look at theorem 7.5. All right, Toby, could you read that?
If lines K and M are parallel, then a reflection in line K followed by a reflection in line M is a translation. If P prime prime is the image of P, then the following is true. 1. Line P prime is perpendicular.
P double prime.
P double prime.
So P double prime is perpendicular
Why did they have
to
do
K and
that?
M. Okay.
2 P double prime equals 2D, where D is the distance between K and M.
Why?
Okay. So do you guys see this?
Yep.
Does this make sense? If you look at those lines, okay, so you know that P and P prime are equidistant from M, right? And then when you reflect it again, you know, you're going to have, you know, double that. And it ends up being that distance then is going to be double that. It's going to be 2D between the original and the end. Okay. All right, so cover up the solution on example 1. All right, now analyze this figure right here. So what's the pre-image on here? HG, and then you have kind of 2 images, right? After 2 reflections, one in AB and one in line CD. All right, so it says name some congruent segments. So let's take a look at HB. What would be congruent to HB?
HD? No.
HB.
GC.
H prime B.
H prime B. Okay, because it's a reflection, right? So it's going to be reflected. Okay, so what else is congruent? Like, let's say,
A
and G.
and AG prime.
okay, all right. Now, what about,
Would H prime and H double prime be?
so HD, right?
H prime D.
And then H double prime D. Okay, does that make sense? You guys seeing it? Okay, and then what else? G prime C.
BA and DC are congruent.
Yeah. And how do you know that?
They're parallel lines.
They're parallel, and then
The
also
parallelogram.
then you got a parallelogram. You know, G. All
It's
the
a
rest of them are
rectangle.
there. Okay, and what is the length of G double prime?
So what's the answer? Why is B?
What? I'm sorry, I don't understand your question,
What's
Luke.
the length of G double prime?
No, B. Does AC equal to BD?
Oh, AC. Yeah, AC equal.
What was the explanation for that?
'Cause it's
AC equal
parallel.
BD, yeah. I mean, they're parallelogram. They're making
It's
a
equal to
parallelogram.
14. GG double prime.
Okay, so
GG
Yeah.
double prime is 14.
Okay, all right.
essentially,
Oh, we have all these explanations during
yeah,
homework. So I'm wondering.
this is a linear theory here, so therefore this angle is also a right angle. 4 right angles make this a
Rectangle.
Okay.
Therefore, opposite sides are congruent.
All right, now let's take a look at G. Okay, Garrett already figured this out, but I want to make sure you guys are caught up. What is the distance between G double prime?
AC, 2 AC.
What's the distance?
What's the distance?
Okay, so
5.
you in a way you're going to have to. Okay, so you
You
know.
have to add.
So it's
Okay, in a way you have to look at the opposite line. You're going to have to look at the line across from it. Okay.
fifth.
You guys know that H
14.
double prime is congruent to G double prime, or the same distance. Okay, so you know if you've got 5 on the other side, you got 5 there. The other one you got 2, you got 2 there. So you're gonna have 14. Okay, does that make sense? All right, now we're gonna get into we're getting ready to set up for how to do a translation.
That's
There's-
2, which means that's 2. So 5, 5, 2, 2. So you have the 5 there. Okay.
Because you know the opposite line is going to be the same length as the one across, right?
It's gotta be equal, and that's a function right
Vector.
there. So it's gonna be
Do you see that, Toby?
Um,
See, look at on the top. You see where it says HB is 5?
yeah.
Okay, so that you know that BH prime is also 5, right?
Mhm.
Okay, so that's 10. And then look at the end from DH double prime. You know that's 2.
Mhm.
So you know that then H prime D is got to be 2 also. And then you know that whole opposite side is going to be the same distance on the other side.
Okay.
So it's 14 there, so it's got to be 14 on the other side.
translation.
Oh, wait. Oh.
Oh, G prime prime. Sorry, I was looking at G prime. Not
Yeah,
G
yeah,
prime.
no, they didn't give you
G-
any
G
markers
prime.
on that side, so,
Yeah, sorry, I was
okay.
looking at G
Wait,
single prime.
Okay. All right, now you're going to learn a couple of notation
Vector.
things. Okay, we're getting into vectors, which is kind of interesting. I like
The
vectors.
vector.
I'm learning about vectors, like a vector quantity in
Yeah.
science.
Yeah. Oh, yeah. It's used
Like
in all
the
kinds of places.
Velocity.
Yeah, and like
Vectors.
like doing figuring out navigation and stuff like that of planes and wind speeds and stuff like that. All right, so right here, let's look right below example 1. It says translations in a coordinate plane can be described in the following coordinate notation. So this is one way to do this. So this is called coordinate notation.
Disappointment.
Okay, so what they say is you have a coordinate x, y, and it maps, okay, onto, it'll say whatever x, plus or minus some quantity a, and then y, plus or minus some quantity b. Okay? That's one way. This is coordinate notation. So you should know this notation because there's also going to be vector notation, and they're saying the same thing, but it's slightly, they'll do it differently. All right, so it says right here, in this example, they're showing that x plus 4 and x minus, they're saying xy is mapping here. So basically what you're going to do is you take your original coordinate, is everybody listening?
Yep.
And then you add 4 to the x and you're going to subtract 2 from the y. Okay.
So you just add in your A and your B.
Okay, so let's look at example 2. And actually this one is going to be subtracting 3 from x and adding 4 to y.
So we're trying to find the.
So you're doing a translation. So what's your image in example 2? What is A, B, and so what's your coordinate for A?
What?
What's the coordinate for A?
1, 3, or -1, -3.
-1, -3, is that correct?
Yes.
Okay, so A prime, is going to become what?
What example? What example? What are the
Example 2.
Example
What are the coordinates?
So
A is.
Okay, so what are we going to do here? We're going to subtract 3 from -1. So -1 minus 3 is
-5. Or
-4. And -3 plus 4 is?
-7. Or 1.
Oh, +1. Okay, so -4, 1.
Oh.
Okay, so that's where it's moving.
So
Okay.
you do every single one.
Yeah, so B is 1, -1. Okay, so we subtract 3 from it, so what do we get? B prime is going to be where? 1 minus 3, -2, -1. Okay, so that's 3. Okay, you see how that works?
Yeah.
All right, so that's a translation. This is using coordinate notation. Okay, so
Mrs. Smith, there's something on here. It's like vector calculator.
yeah, I'll have to look at it. I haven't really used that.
I've never played that calculator. Like, James could do like all of the math problems on his calculator.
Well, you should. Well, you can do. There's something. You'll learn some of it. Okay. All right. Now, let's go to page 423. Let me see if I can wrap this up here. It says another way to describe a translation is by using a vector. A vector is a quantity that has both direction and magnitude. So in other words, it's going to have a direction that's going, and then based on how long it is, it tells like how much magnitude it has. Magnitude is defined by its distance. Okay. All right. Now this is the thing that's important. It says the diagram shows a vector. The initial point is the starting point. That makes sense, right? And where the arrow ends up is the terminal point, okay, or the ending point. So in this example on page 423, P is your initial point and Q is your terminal point. To figure out, the distances and stuff like that, you're always taking the terminal minus the initial, okay? And also take a look at this. Now, it has a horizontal distance that it's moving and a vertical distance. So in this case, the horizontal is what? 5 units to the right, and to get from P to Q is 5 units to the right and 3 units up. All right, so the coordinates, to have this, to show this in vector form, you would say vector PQ, and this is the other thing they do. They show, it's almost like array, but it's like a half array, okay? And they show, this is in vector form, and what this is going to do is it means that this vector is, and they have like these little pointy brackets. This is the horizontal, and that's the vertical. So that's the horizontal change, and that's the vertical.
PQ.
Like X and Y. Okay.
Okay, and this is in vector notation, I guess is what they call it, or component form actually, component form.
No.
So you need to
Yeah. So, but that's easy to remember. So it's just like 5x 3y.
well, so these are sort of doing the same things, okay? But so you're gonna have to pay attention in the directions when you're doing the homework, whether they're asking for something in coordinate form or component form.
Right. It's like xy, except the origin is the initial point. Like it's like.
It's sometimes you'll see. Okay, so let's take a look at example 3. Cover up the solution there. All right, now so tell me what is the horizontal change on
3.
A?
What are we covering up?
So JK, well, example 3. Okay, so what's the horizontal change from the initial point to the terminal point? Which direction are you going in?
3.
Positive 3, right? So the component form for JK, vector JK, is 3 for horizontal. What about vertical?
4.
And it's positive 4, right? Because it's going up. Okay, all right. So what's the component form for B?
X.
Okay,
Zero,
is
X
there
plus
any
0.
horizontal change in B?
No. X.
So no. So what is that if you don't? There's no horizontal change. 0.
Oh, 0.
0. Now and then you're moving up vertically. How much?
3.
5.
4.
So vector NM is equal to 0, and then you're moving up. Did you say 5?
1, 2, 3, 4.
4. All right. So it's moving up 4. So this is what it looks like in vector form. Okay. And then the last one's TS. Okay. Now where's your initial point on TS? T. So so the horizontal is which direction? Left or right?
Right.
Right. So that's positive what?
3.
3. Okay. And then what are you doing?
Negative 3.
And then you're going
Positive
down
3.
3. So this is going to be TS. All right.
So it's 3 negative.
And it's 3 negative 3. Okay. Now,
Why-
sometimes they're going to give you coordinates of both. Remember to get you're going to have coordinates of both of those. You're going to subtract. You're going to take your terminal minus your initial. Okay, you're going to take the x of the terminal minus the x of the initial to get the right, because you want to have the right direction where you're going to be going. Okay.
Why do we use the pointy brackets?
So, because this is the notation to indicate that you're looking at a vector.
Okay.
Okay, so this is the vector notation. All right, so let's look at example 4. We get out here at 4:40. Yeah. All right, so let's see if we can get this done. All right, it says the component form of vector GH is 4, 2. Use GH to translate the triangle whose vertices are 3, negative 1, B is 1. Okay, so basically you need to translate each of those. Okay, so what's A prime going to become without looking at the diagram, but looking at the initial vertices, which is 3,
7,
negative
1.
1.
No.
So you're simply going to do what? You're going to add 4
And
then add 2 to that. So 4, so you get 7 and then 1. Okay? All right, somebody else do B.
Okay. 5, 3.
Okay, and then C is somebody else.
7.
No, C is C's going to be okay, I'm sorry. Yeah, 7 what? 7, 7. Yeah. Okay, and there you go. So that's how so that has a vector, and it's taking that whole triangle and it's pushing it in that direction. Okay, it's pushing it horizontally, whatever 4, and then vertically 2. All right, go to example 5 on the next page.
Oh,
Okay. All right, now, you're given an image and a preimage. Okay, the blue is a preimage, and you want to describe the vector that caused that translation. Okay, so cover up the solution on that. Let's take something like S. Okay, and then look at S prime. All right, so you take your terminal and you subtract it from the initial. Okay, so if you went from S to S prime,
Negative 8, 2.
so it went negative 8 in that direction, right?
Yep.
So it's like saying negative
Yeah,
4
negative 8
minus 4. Okay, so that's negative 8. And then you went 4 minus 2. Okay, so it's 2. So, okay, do you see how that works? Because
cool.
okay, so now that vector then that moved that trapezoid
Yeah.
would be, well, you'd have little pointy brackets, right? And you would say -8, comma 2. Okay. All right. So now, last example. Example 6, navigation. This is where this is used a lot in. Okay, vectors are used in navigation. Okay, Andrew, would you read the top of example 6?
A boat travels a straight path between two islands, A and D. When the boat is 3 miles east and 2 miles north of its starting point, it encounters a storm at point B. The storm pushes the boat off course to point C, as shown. A. Write the component forms of the two vectors shown in the diagram. B. The final destination is 8 miles east and 4.5 miles north of the starting point. Write the component form of the vector that describes the path the boat can follow to arrive at its destination.
All right, so let's talk about what's the vector AB going to be? You went from 0, 0 to 3, 2.
3, 2.
So it's 3, 2, right? Okay, and then to get from
1,
B
0.
to C, what vector was that?
1, 0.
So you went, no, but it's, yeah, so it's that's right, it's going 1 up, right? And,
CD is 4,
Uh,
2.
okay, so it's 1, 0, so that's it. And then
4,
CD, you got to go from 4, 2 to 8, 4.5. So what's your horizontal vector, horizontal component going to be? 4,
2.5.
2.5.
there you go. Okay,
Are we going to the other form at some point?
are we going to do what?
Are we going to do the what do you call it? Other form was coordinate form?
Yeah.
Yeah, I mean, so just look at your, make sure you look at the questions in the homework, and and you'll see. And then let's take a look at what's due on Thursday.
I never quite understood coordination.
Should we have another algebra?
Do you write it down as
Coordinate
X plus
notation. It's called coordinate.
But how do you write it down? What example?
It would be
sure
it would
we'll
look
look
like this. It would have x, y, it'd have a little line, and it would say x minus 3, comma, y plus 4.
Now would it be
That's coordinate notation.
simplified so that X would be whatever X is minus 3?
Well, you'd have your initial points, and you would basically be subtracting 3
Can you show
and
me a
adding
real,
4.
a real like example of like an actual number?
Well, they would say, you have A is at 3, 4,
It's
and
the
then
same
using
thing as
coordinate
vector.
notation. It works exactly the same thing as vector. It's just a different
Are
notation.
you supposed to go and subtract the whatever 3
Yeah.
minus 3?
You would
It's
get an
just
original vertice. Yeah, and then you would just give the coordinates.
I'm
So
just
we
wondering,
have-
are you supposed
so-
to simplify it?
For Thursday, we have an algebra
Yes.
review.
So go ahead and take the X, whatever it was.
Exactly.
Okay.
You would simplify it.
So
Yes, there's an
so-
algebra review. So you're doing part 2 of of what you did part 1 of.
And homework 7.4.
That's it. Okie doke.
Yeah, no, the Canvas app works so well. They literally just use hit to do and it shows all the homework.